Then the problems can have discrete search space. The most interestingly, they may have mixed. Some of them can be discrete, some of them can be continuous permutation, and then you need very flexible algorithms for handling all these different kinds of complexities. Large dimensions. I mean, we have solved some problems going to 1 million variables, but pretty easily you can have 100 variables in an optimization problem very easily. 100 to 1,000 is not very uncommon these days, but you need methodologies that may sometimes take even more. Like I said, may not be million, but maybe few thousands in solving practical problems. Same thing is the objectives and constraints. Of course, you cannot have 100 objectives and try to look into the problem, although there have been a lot of efforts going on now in trying to handle such large dimensions. But we very recently talked about and working with 10 to 15 objectives, which I will talk about in the next lecture. Those we are calling as evolutionary many-objective optimization. Constraints are likely to be nonlinear. Multi-modalities, there can be lots of different optima that you have for your objective function. So how do you handle these things? Multiple objectives I'll talk about in the next lecture. And uncertainties in decision variables. You do all this effort doing this optimization and find a nice solution which is close to being optimum, and then you have problems implementing it, because when you try to go and implement, you find that there are machine tolerances, there are some uncertainties inherent to the system, environment changes, the temperature, humidity changes in a system which you didn't predict, and then what you found as an optimal solution is not optimal anymore. So instead of finding optimal solution all the time, you should be then looking for what is known as robust or reliable solutions. So you should be able to do and changes to your optimization algorithm and find those solutions. There are lots of problems in practice that are computationally expensive. That means when you evaluate a solution, maybe it takes few hours. I have solved some problem, one solution evaluation takes almost a day. So if that kind of problem you're trying to solve, you can't wait 1 year to have an optimization run finished. You need to be able to do, in those cases, maybe in a few days, maybe at most couple of weeks. So these are something very important changes in the optimization literature when you're trying to look at solving very large computationally expensive problems. And then, of course, at the end, no problem in practice coming from one particular discipline. You take a problem, you need to have mechanical engineering aspects, you got to have electrical engineering aspects. If it's flying, you got to have aerospace, aeroelasticity, aerodynamics, all these would come in. And so a problem should be looked into from various different disciplines, and then you need to be able to coordinate. You need to be able to get objectives, constraints, and variables from various disciplines, and then how do you coordinate the whole issue becomes a problem. So this, what we're talking about, are real practice. So optimization problems are different from one to the other, and there are so many different complexities that comes in, so you need to have a very flexible, simultaneously efficient algorithm. So if you look at the classical way of doing it, I'm not going to spend a lot of time here. The way things have evolved is that in the very beginning, I would say before the Second World War, or even before, optimization had been there for many, many years, right? They were using exact optimization. So they would actually use the exact optimality conditions to come up with a solution. You could do that only for limited problems. So really during the Second World War, people had used optimization in practice, particularly in the war-related resource allocation kind of problems. So numerical methods came out at that point. And most of these methods have this property is that you start with one single point in the search space, and then the algorithm suggests a direction for you to move. So from one point in the initial guess, you move towards a particular direction and go and find the best point along that direction. Once you found the best point, that's the end of one iteration. The algorithm suggests you another direction to go, and then you go in that direction, find another best point, and so on and so forth. So you do this in iteration. One point, moving to another point, moving to another point, and hopefully you're hoping that all these points are eventually taking you towards the optimum. Okay? So that's how the classical methods work. There are some methods which works with number of points, like the top one. It's called Nelder and Mead search methods. Have been quite popular. I don't see it being used very often these days, but still it has some nice properties, is that you start with not 1 point, but a few points. Like in the case of 2 variables, you start with a triangle, and then this triangle changes. So you look at these 3 points on the apex of the triangle and try to figure out which one is the worst, and then you go away from the worst towards the better solution. So your triangle changes its shapes and sizes, and eventually these triangle flip-flops and finally come close to the optimum. Okay. Then there are other methods that are gradient-based. You're actually using the negative of the gradient, which is called the steepest descent method, and that will take you, if you follow these for simple problems with having just a single optima, these methods are very difficult to beat. But if you have multiple optima, if you expect that there are few optima in your functions, then if you're using some of these algorithms, you need to try it many times, because they can get stuck at a local optimal solution. So instead of giving you the best solution in the search space, they will give you a local optimal solutions. So there are certain limitations like that. But there is a nice theorem that came out in '97, which I would like to just tell you. It's not very practical, but if you keep this at the back of your mind all the time, if you're working in this, that really helps. It's called no free lunch, and actually it means what it says. So it says that if you are solving all possible problems that you get today, get tomorrow, or any other time in your lifetime, and you are taking 2 algorithms, one can be the very best algorithm that you had developed, another could be a random search method, for example, with some optimization tint in it. It says that if you apply algorithm A1 to all these problems and define some kind of a performance measure of how well it did, and then you apply the algorithm 2 on the same set of problems with the same number of resources, that means on the same computer, the same number of time you're putting to solve each and every problem, their conclusion after a lot of mathematical treatment says P1 is equal to P2. That means the 2 algorithms cannot be differentiated if you're interested in solving all problems. Okay? So that's a good thing to know at the back of your mind, instead of making big claims saying, I have designed an algorithm which can solve all problems better than any other algorithm. You are making a mistake, because somebody will point you out to this theorem and says you cannot state that statement. But what it also says is that if you narrow down your problem, so if you're not interested in all problems, you say, I'm only interested in solving linear problems, or quadratic problems, or convex problems, or constraint problems of certain type. As soon as you specify your class of problem you're trying to solve, then this theorem breaks down. Then there can be one algorithm better than other algorithms. So after these theorems came out, people have been very careful in claiming what they're claiming in the paper. Okay, so it's good to know at the back of your mind. Now, getting back to the computational intelligence area, and the evolutionary computation is what I'm going to now talk the rest, is I just wanted to put you the evolutionary computation in the perspective of the whole computational intelligence area. So basically, there are 3 main topics under computational intelligence. By the way, IEEE now has a society on computational intelligence called Computational Intelligence Society. So they have recognized that this as a field, and there are quite a few journals under this society. There are big conferences and a lot of things going on in that. So neural networks, evolutionary computation, and fuzzy systems. So these are the 3 main components, although there are many, many other not so big, but other areas also part of computational intelligence. So evolutionary computation is just one part of that. And under evolutionary computation, there are many, many topics. Some of them may sound very similar to each other, like evolution strategy, and evolutionary programming, evolutionary computation. There looks like juggling of similar words, but they are essentially different somehow from each other. And in this lecture, I'm not going to cover everything, but I'm going to show you mainly the genetic algorithms, which is how this whole thing has started back in 60s. But there are a lot of many recent ideas. So if you're interested, you can Google and look at some of the introductory stuff on it. Okay. So why should we follow evolution? So all these evolutionary methods have these principles that they mimic what goes on in nature. Why would we follow? Simply because what we see around us, which has been designed by nature over many, many years, seems to be close to being an optimal. In my optimization class, I give actually an assignment that show that if you are minimizing a structure with the minimization of weight divided by the strength, that means for a unique strength, I want to minimize the weight of a structure, the hexagonal shape comes out. You can try all different shapes, starting with triangle, square, pentagon, hexagon, all the regular polygons. You will see that hexagon comes as the optimal structure. Why is it? Well, there are some mathematical reasons. When you do the optimization, you use those principles, and you see that that comes out. But the question is, how does bees know that? Because bees cannot do mathematics, right? But how do they figure it out? They did, after a lot of trial and error, and there is a evolutionary guided principles that they have been following. That means something that worked a little bit better than what it is now, they would then build the rest of the thing from on top of that, right? So there's been guidance that something that works should be given more emphasis, should be continued with that. Something that didn't work, forget that for the time being. So there is a guidance in that kind of an evolutionary search. In terms of Darwin, that was the survival of the fittest idea. And there are so many other very fit, looks like an optimal design that we have. Of course, what nature is doing is not a static optimization where everything else is fixed. It's very complex than what I'm just telling because of the changing environment. But then we have a similar optimization context in practice, which are called dynamic optimization, online optimization. So if you're trying to develop algorithms for those, maybe you need to go close to what nature is doing in trying to have this adaptive evolution that's going on. But there are good reasons to mimic these natural evolutionary principles instead of going through the hardcore mathematics way, like using the gradients and first order or second order derivatives or KKT optimality conditions, for example. Another reason why we are going through all these is that we see that since the dawn, we have been doing things in a manner that seems to be evolving, right? So if you look at telephones that has been evolved over the years, the aircrafts, the cars, or the mobile phones, there had been a history of evolution. So if you see that what was there a few years ago, 100 years ago, and what it is now, there has been constant change. And why is this change? Because of the new technologies that came up, because of the new science that are available now, the new computers to do lots of number crunching than it used to do before. So we could do more and more. So it's an evolution of things, right? So if we follow this principle, then let's say we are trying to come up with what is the best looking mobile, what is the best performing mobile that we have right now, and say there was an algorithm that took place many years ago and they're evolving, you will probably come to what we are, what we call as a mobile today. So there are evolutions that we see around us, and there is natural evolution that we see some good designs that are around us. So all this gives us confidence that if we can mimic this process, we probably able to come up with a generic methodology to solve these kind of problems, right? So the genesis of evolutionary computation starts with Darwin's survival of the fittest idea. And one other thing is that instead of having a point, moving to another point, moving to another point, here we are interested in taking a population of points, moving to another population of points, maybe an overlapping population, and then another population of points, and so on and so forth, eventually going towards the optima. So if you think of an algorithm now, if you want to do it on a computer, it'll probably look like what I have on the left side, that you start with representing your solution, and then with a iteration counter, we're starting, so that's equal to 0. And then you start with a random initial population. Often we do it random, but if you're solving a practical problem, you already know some good designs, good solutions. You can actually start with that biased population. And then what you do is check for a termination condition. If not to be terminated, then you use that population and choose few good solutions of it. That's called the selection. And then you change this population using series of operators called variation operators. And then that's called the offspring population, P-T. And then you evaluate these new solutions that you have created. And then you combine the offspring population with your previous population, which we call as the parent population, and keep the survivors, keep the good ones from it, increment the counter, and go into this loop. So if you write a computer program with such a method, it can be very small or it can be quite large, depends on what kind of bells and whistles you are going to keep on this. In fact, there was a competition a few years ago in our annual conferences to say who can write a genetic algorithm code with the minimum number of lines. You can use any programming language, so they're just counting lines. There was some description of what it means by a line. And who can write a code that will work with minimum number? Guess what? There was a 17-line code that won using MATLAB. So you can actually implement these ideas very simply and then can solve some real problems. But of course, that's for the competition. But if you want to, I would not be using that code for solving the industrial problems that I'm solving. But just to tell you that ideas are simple. You don't have to be very complex here. But customization is the key, as I will show you with some of the examples. So what happens when you do this is you're starting with a set of points like I'm showing there with a set of black dots that you see there. That could be your current population. And then what you're doing is you're selecting few of them from it, which are supposedly the better ones. And then you use this to create new population member. Let's say those are the open circles that I'm showing. So open circles are the offspring population, and the black circles are the parent population. You combine them together and keep the better half of that. And that I'm showing with the circle. And then this circle will keep on moving towards the optima. So if everything is got right, what happens? Actually, two things happen. One is that some kind of a representative point, let's say the centroid of the population, for example, it moves towards the optima, and the variance of the population reduces as you go towards the optima. So these two things usually happen. I'm going to just show you the very simple example of how a binary coded genetic algorithm that Holland suggested. John Holland was the person who actually first conceived this idea of GA back in 1962. The example, of course, is not taken by him. I'm taking the example, but I'm actually following his algorithm. So let's say I have a very simple problem of designing a can with two variables, diameter and height. So if you give me a diameter, give me a height, I can compute how much it would cost by just calculating the total material I'm putting to make it. So there is a circumferential area, and there are two leads, okay, which is a function of D and H. And I want a volume inside to be at least something. So I'm saying the volume should be at least, let's say, 300 milliliter. So I'm planning to design a Coke can, for example. All right, so one of the thing you do in a binary coded GA is instead of representing the diameter and height in actual real numbers, you represent it in binary strings. That's why it's called binary coded GA. So I'm showing you a binary string right there. And as an example, when you decode this string, you get the diameter is the first 5 digits, 5 bits, sorry. That gives you a number 8. And when you take the next 10 bits, next 5 bits, you get the height. That gives you 10 in this particular sense. So you'll have, let's say, 10 centimeter and 8 centimeter. You can then plug in your objective function and constraint and see if it is feasible. If it's feasible, you assign the fitness. So this number 23 I'm putting there is how much it costs. So that's the function, that's the value I'm trying to minimize. You could actually do a very generic mapping with the X from the string that you have, the S mapping to the string, knowing the upper and lower bounds of these variables. So let me not go into the details of that, but that's how I represent it. The next step in an evolutionary method is to create a set of random populations. So here I've created 6 population members on the left side, as you can see. I'm not showing you the actual diameter and height, but I'm showing you how much they cost and their shapes. Now, the left top of left 4 of them are all specifying that volume that's specified is actually satisfying that. But the other 2 do not have 300 milliliter volume. So I'm putting a penalty there, this additional cost of 28 and 33, 35, I think, to penalize those 2 solutions, okay? But now what I do is go into a selection mode. So to do selection, what you do is take these 6 solution population members, put them in a random array, in a random shuffling manner, like you shuffle a pack of cards. Very similar way, you shuffle these 6 members. So I have a random order there on the left side. Now you take the first 2 and decide which is better based on its fitness or the function value. So here I'm minimizing the cost. So 23 is better than 30, so I choose 23. I take the next 2, 30, what is that? 24 is better than 39, 11 plus 28, so I choose the 24 one. Similarly, I do one more time. So this is how I've created half the population. I've actually used and created this mating pool with half of the population members. And then what I do is I take the same set of 6 members, shuffle it again in a random manner on the right side and repeat this tournament selection process 2 at a time and create the next 3. Okay, so that's how you see I get the good solutions. The 23 solution is the best in this population. It got 2 copies now in the mating pool, in the intermediate mating pool that you see. And then the worst one, which was 9 plus 35, that doesn't have a copy. And these are not magic, because the first one is the best, so it'll win both times. Second, the 9 plus 35 is the worst. It's going to lose both times. So what you end up getting in the middle are someone's having 1 copy, someone having 2 copies, and someone did not pass through. So that's exactly what Darwin said about the survival of the fittest idea. If you're good, you are going to survive and probably have duplicates. And if you are bad, you're going to die, and you're going to not be taken into the next generation. So that's what happens. So if I go back, so I had this population on the left to start with. After I applied tournament selection, I get the population on the right. Okay, so there are some individuals made 2 copies, some no copy. So with this process, I have not creating anything new. Now comes the chance of doing crossover and mutation. So in the binary coded GA, crossover is very simple. You pick these 2 individuals at random and put a cross site somewhere and swap the information on the right side of that cross site. Okay, and you create 2 new designs. So that's how you're crossing. You are recombining 2 good solutions into 2 children solutions. And in a mutation, you just take a bit at random and then make it to its complement. So you see that the left-hand side one gets mutated to the right-hand side one. Both this you do with a probability. Crossover you do with a probability called PC, crossover probability. You don't want to do it to 100% of the population members. This crossover, but we do it with a large probability, like 80% or 90% of the time. Mutation, you want to do it with small probability, like we do mutation so that on an average, 1 bit in a whole string gets mutated. Okay. So the combination of all these things is the selection, the tournament selection operator I mentioned, and the crossover and mutation works. Tournament selection, as you see, is picking up good solutions, and crossover and mutation is taking these good subpopulation and creating hopefully better solutions. And this process continues. Unfortunately, I cannot run the videos here. I just tried, and it's just crashing, so I cannot show you those videos. But these kinds of methods has been there, as I said, since 60s, right? Lots of applications has been there. Some of these they cannot mention because of the proprietary issues, but there are few that leaked and are available, and sometimes they are proud to say that we have used a genetic algorithm or an evolutionary method to solve it. Here are a couple of examples. One is the Japan's Shinkansen, which are the bullet trains. In 2007, they came up with this new series called N700 series. The nose of this bullet train is designed using a genetic algorithm. Not because they just want to use a different method, but they had to. They tried classical methods, and they were not successful in getting a design that they were looking for. Because in Japan, what happens, most of the train lines go through a crowded area because there is not much in the interior. People usually live in the coastal area. So all the trains go through this very heavily populated area through tunnels. And so the problem is not to have cost minimization or anything, but they want to minimize the vibration that it causes on the tunnel, because that shakes the houses, make a lot of noise. So their main goal is to minimize that. So once they designed it using a classical method, they go to the wind tunnel and check it, and it was not satisfactory. So then they came to know of GA, and then they used, and they found successful results. So all these are saying that the GAs have some abilities that the classical methods may not. And it is those abilities I was talking to you about, that they're being flexible, their chance of not getting stuck in local solutions. Maybe the classical method they were using were getting stuck at the local solutions which are not acceptable to them. Then the Kone, the Finnish company, with the in their multi-car elevator system, you are going and pressing the button at some floor, like that many other people are doing. Every half a second, it registers all these calls and then runs a genetic algorithm within half a second, and it's churning out what is the optimal allocation, which car should go to which floor. And then again, after half a second, it's done again. So since it has to be done so fast, they're not actually running the code at that point. they have made electronic chips which actually runs the genetic algorithm very quickly for a few generations and comes up with an allocation. So you can see that genetic algorithms as a landing calls is there in their flowchart where they're using these methods. And again, these are just two methods. Just to tell you some ideas of when this has happened, you know, how this has kind of evolved. So as I mentioned, John Holland, his picture you can see there, he's still somewhat active. He's not that much active. He's over 80 years now. But he's still in Michigan. So he was the first person who had this idea. He wrote his first book called Adaptive and Natural Systems, called ANAS, in 1975. But till that time, he worked with many of his students to develop this field. There were another group of people in the West Coast who were working on very similar ideas called evolutionary programming, led by Larry Fogel. And then on the other side of Atlantic, in Germany, particularly in Technical University of Berlin, Professor Schwiffel and Ingo Rickenberg, they were the people who were developing a method called evolution strategy. So the difference between the evolution strategy with the other methods is that evolution strategy did not use any crossover or recombination kind of methods back then, but now they do use. So these three different ideas almost at the same time were being researched. Only in, I think, 1993, that they first realized that they're doing similar things, and then they came together and started this idea called evolutionary algorithms these days. It's 1991, sorry, that has first started. Okay, so, but if you look at from the optimization concept or the context, it was Kenneth DeYoung, who is now in George Mason University, but he did his PhD with John Holland in 1975, and his thesis actually first time showed that a genetic algorithm can be used as a function optimizer. Okay. Then came David Goldberg and his book called Genetic Algorithm in Search, Optimization, and Machine Learning. This morning I was searching some of the citations in this area. His book alone, that single book, has 65,000 plus citations so far. It was considered for a best-selling book at some point, but marginally lost. But you know, it's one of the main reasons why this field have taken off, and I'm very proud to be a student of him and had the opportunity to work with him. Then came a lot of conferences, and the first one was in '85 in CMU, and then it is still continuing. Now, of course, it's taken a much bigger shape. It's called Gecko. Then the theory-related workshops came out called FOGA. First journal came out in 1993 from MIT Press, and then 1997 from IEEE, called IEEE Transactions on Evolutionary Computation. Look at the impact factors, 4.69 and 2.63. These are very high, one of the top journals in computer science area. Then we have these big conferences, Gecko and CEC. They are regularly being held every year. So that's how it has started. That's how we are. Very fast these things have gone, and a lot of applications and theoretical work that goes on. My experience with this is that these problems you should not try in each and every problem that you face. So you try them where your usual methods have failed. I always try to use some existing optimization software from MATLAB, KNitro. There are some of these Cplex, for example, that are available. I first try them. If I cannot solve them to my satisfaction, I then go and use these methods. Okay? And there are lots of reasons why these classical methods will not work. Any kind of complexity I mentioned, you know, makes them kind of not an obvious choice. Then you have to think of other things to do. And there is a class of problems, which I'm going to spend a lot of time on the second lecture, is solving multi-objective optimization. So you're looking for multiple solutions, not just one optimal solutions. Then, of course, these methods do not have any competitor. Other kinds of problem where instead of solving the problem, you are trying to solve a concept. For example, again, I can't show the video, but here the robot is trying to go from one point to the other point by avoiding obstacle, and you want to come up with you know, some kind of a rule-based system that the robot will use and navigate online. So you try to come up with now some concept of how to solve the problem, but not actually have the information about all these obstacles and find out the path that will be optimal. Or you are doing this kind of L system design, where you need to know that how can I get to something from a simple concept, and then you work in this concept space and try to come up with a concept for solving the problem. So this kind of cases, I think evolutionary methods are excellent. So 3 main advantages, why they work well and why you should be thinking of them. One is the population approach. So that gives them flexibility, that gives them the safety in number, that gives them all these other kinds of problems like multi-objective, multimodal, bi-level, which you can solve so nicely. And then, of course, the operators are flexible. You can change this tournament selection, the crossover operator, the way you think would be best for this problem. Or you can even change the whole algorithm. Instead of doing mutation after crossover, you could do mutation before crossover. Selection maybe after crossover is mutation is done. So you can change the whole algorithm. You could put in some more features into the algorithm. But take this concept to a classical method, you can't change anything. It's all God-given. You can't change. So if your algorithm, the classical method you're trying to solve, did not work to a problem, all you have to do is look for another method. You cannot modify that method too much, right? So you can stay within one method in this particular case and try to make it to work for the problem that you are trying to solve. But these flexibilities come with a price. What is that price? That the customization is the key, and you need to be able to customize it well. You need to be able to understand what works and what doesn't work. So if you know from me today what is evolutionary algorithm, I'm not expecting you are an expert tomorrow. It just requires a little bit of time to know what things work, how things work here. So there is a price that you have to pay because you're getting a very flexible system. Okay, so I've talked about so many things. Let me show you now some concrete examples of how these things work. I've showed you a couple of examples, but these are where I was involved. So this problem came from Spain. It's a power company there called Endesa. They were, a few years ago, they were interested in going for solar because Spain gets lots of sun, and they were interested in having solar power captured and developed and then distribute as well. So to start with, they had a project where they were trying to figure out 3 variables: how much solar collector area we should have, how much storage capacity we should have, and how much auxiliary boiler power we should take, because someday can be cloudy and then you cannot rely on suns, and so you have to have some auxiliary way of doing it. So, but so it's a three variable problem. So if you talk to some people who are used to with optimization, they would say, what are you talking about? Only 3 variables? I can solve it any day. But I'll show you the problem complexity that comes with it. The problem is they are not going to give me the formulation, the modeling, because that's proprietary to them. They're not going to give me how these objective functions are derived from these 3 variables. Rather, they would give me an executable and say, okay, in this executable, you put these 3 values, any three values you want to put for solar collector area, for the storage capacity and auxiliary boiler power. After about 3-4 minutes of running on our computer, it churns out one number. That's called the objective function. That's the profit that this is going to give them. If the profit is negative, that means it's an infeasible solution. They cannot accept it. So it's infeasible solutions. If the profit value is positive, that's good. That's a feasible solution, and the number there tells you exactly how much profit you're making on this. And they asked me, can you optimize this and tell us the maximum profitable solution? Sounds easy, right? But the black box optimization is very difficult because I can't see, is it quadratic problem? Is there some multimodality? Is there some discontinuity? I can't see anything, what is going on inside that source code. All I have is a problem description, very abstract problem description like that. So when you get such a problem, you actually try some standard software, as I said, right? So we purchased some software called LGO and Lindo, and we are trying to use this method. We were very, very disappointed. We run some of these methods starting from some initial points, and the Lindo gives us some values, but they are all changing. It's so dependent on the initial point that I'm giving them. So obviously, now I'm doubting whether any of these that the Lindo is giving, are they close to being optimal or not? Then I tried the other software. It does even weird. It always gives me the same solution back. I don't know what it is doing inside. And I didn't have the energy to really go and fix that code or anything, because this is something we purchased. We just wanted to see. But these are some snapshots I'm telling you that when you try to use a commercial software for optimization to solve such real-world problems, particularly with black boxes, there's not much you could do because there's not much information you have. Either it works or it doesn't. If it doesn't, you have to just leave it. Okay? So to understand further about the problem, what I did is I randomly evaluated 10,000 points, 5 sets of 10,000 points. And from these one set of 10,000 points, I take which is the best solution. and then I try to look at here. You see these solutions that I've printed there, they're all different, right? Quite different from each other. That actually tells me that this is probably a highly multimodal function that we are looking at. And then I do a systematic study of keeping two variables same and one variable I change, and you see that apparently it looks like as I change this variable AC, I increase it, my profit function increases. So that means if I increase my solar collector area, my profit goes up, which makes sense, right? But if you focus on a very narrow part of that fitness function or objective function, you see the multimodality that appears. So it's just like, it's a massively multimodal problem, and that's what's happening by those classical softwares. Wherever I'm starting from is just going and giving the nearest optima, the nearest local maxima. If I start with another point, it just goes up and gives me the next local maxima. So that's how I'm getting different solutions. Okay, so I download a GA code from my website and first try and use it, and I start getting some results. And let me show you, this is the best result that I get with a huge profit, as you can see, some $29 million, or euro, sorry. And then what I do is I try to run it many times, okay, from different initial population, and you can show that the results are not changing much. It's still in the range of 29 million. Every time I run it, I get slightly different here and there. So there is about, I think, 0.11%, 0.11% difference from each other. So I checked to the industry, said, is it okay for you? Because I'm going to give you this code. Now you can run it for other situations, but you are getting about 0.1% difference in every time you run it. Oh, this is okay, no problem. So practice is like that, right? But I was not happy internally. I said, no, I need to get it more consistent results. So I modified the algorithm a bit. Now I do a focusing. So it's an adaptively focused kind of GA that we have. I get a slightly better result, about 0.04% better profit. And then I run it 10 times again. Now you look at these results. Now I'm getting 29,200,000 something, almost the same. So this, the fluctuation here is about 0.0017%, which is, to any practitioner, it's okay. You don't have to do anything after that, right? But the interesting thing happens, why this problem is difficult, is when I look at these three different variables, the first variable you have there, as you see on the top, on the left, is that it is happening at a discontinuous point. The second variable is happening in an isolated point. The one on the right and top, you see that it's happening at an isolated point. If you cannot adhere to that solution, you are bad. But that's the global maximum. And on the third case, it's happening on the edge, the boundary of the third variable. So these are the different difficulties actually we face from practice. And here, accidentally, I came across a problem which has only three variables, but all these usual difficulties that we see in practical problems are all here in one problem, aided by the other problem, that is that I don't have the objective function mathematical description of that for me to gain any confidence. The second case study I'm going to show you is again with a company who does with castings. Every day they are making molds and creating a lot of casting, and they are into the medical area, so very precision casting they do. It's a very well-to-do company, so they get lots of orders. Now think about this. They are melting metal in a 650 kilo vessel. Okay? So 650 kilograms of metal is melted. Now you're going to pour into different castings. You have lots of options. Say you got 4 or 5 or 6 of them casted, and you use 630 kilos out of 650 kilos. 20 kilos are still on your vessel. But none of these castings is less than 20 kilos. So what happens? That becomes a waste. At that point, if you think, oh, if I've done some other combination, maybe I could have utilized 645 kilos. But it's too late now, right? Because you cannot pour 20 kilos to one casting and wait and come back 2 hours later and put the remaining, right? Casting you have to either do completely or don't do it at all. So the question is, you're not doing it one time. One day they were doing 13 times, and they were trying to plan it for the whole month. So lots of such things you have to do. You have to plan how to do it. You cannot do it by hand. In fact, this fellow wrote an Excel code when they first came to me, and after his dinner, he would run it on his laptop. Next day morning, he will look at the solution, and he could see by himself he can change few things, because he was getting about 70 to 75% metal utilization. Although he could see that this can be improved, because he was not using any sophisticated algorithm. He was just manipulating through his Excel software. All right, so then he came to me, and I said, okay, we can have a shot at it. So we modeled, we actually formulated the problem. Turns out it's a linear problem. With my variables, objective function is linear, constraints is linear, everything is linear. The only difficulty is every variable there is either 0 or an integer. That variable says, from the ith heat, the kth casting, how many copies I'm going to make. So I cannot make 1.5 copies. I either have to make 1 copy or 2 copy or 0 copies. So that itself, that it's a linear problem, but you have integer restriction in the variable, that screws up everything. If you didn't have the integer restriction, there are very fast algorithms like the Danzig's method or Kormarkar's method for solving linear programming, right? Very fast. You can go to thousands, millions of variables and solve them. But as soon as you have integer restrictions, you need to use what is called as a branch and bound method, which I'm showing on the right-hand side. And that's an exponential algorithm, which means as you increase the number of variables, it slows down substantially. And we had this experience. We tried to use this for 100, 200 variable version of this problem. With the Simplex, it works tremendously fast and very good results. You go to 500 variable, you already have to wait 3-4 hours. You go to 1,000 variables, about 7-8 hours, and it's a good result. But after that, it just becomes impractical. And remember, in this problem, we had to go to solve 20,000 variables, where we are stuck at about 1,000 variables. So we design now a GA to solve this problem. First, what I did is I downloaded my software from my website and run it. It was a disaster, because it's a linear problem, and I'm using a very generic genetic algorithm. Now, here is the need for customization. I need to develop a GA only to solve this linear problem. The difficulties are the integers, but that's not an issue with GA. So I created a GA just to solve for these linear problems using some innovative ways of doing crossover and recombination. Because of these issues, I cannot tell you exactly what is being done there, but it's a very fast method. And look at here the problem where there are 2,000, it's a 2,000 variable problem I'm showing, and solving it with just 20 variables. But let me show you the final result. The industry is interested in 20,000, or I think about 16,000 variables. So here is a result that I'm showing. On the x-axis is the number of variables. Y-axis is the clock time for solving the problem. Now here, by solving the problem, I mean as soon as I get a solution which is 99.7% metal utilizations, remember the guy was stuck at 70 to 75%, but I put my target as 99.7%. So that means I may be off from my optima with maximum 2 kilos of metal being there. So I could give them a result with 99.7% accuracy, and they require only about 10 seconds to solve it. So they were happy with that. I came back and said, can I publish this kind of work, because I'm quite excited about its result. I think people should know. They said, as long as you don't use our data, it's fine. So we took it and now extended it to a 1,000,000 variable problem. You can see the results, 1 million on the x-axis. And this requires about 30 minutes of time, which is not a whole lot. But look at the way the scale-up goes. It's a log-log plot, so it's linear, so it means a polynomial complexity algorithm. Now, we got a best paper award for this particular work in a conference in France. So there was a smart guy sitting in the audience and said, he looked at my formulation and he said, hey, this is a knapsack problem. A knapsack problem in computer science is known to be NP-hard. That means you cannot have a polynomial time algorithm to solve a knapsack problem. And here I'm showing a polynomial time algorithm. It's actually less than quadratic. It's between linear and quadratic with a power of, 1 point something here. So he was doubtful that we must have done something wrong. And I said, no, nothing is wrong. Any of these points I'm not claiming to be optimum. It's near optimum. It's 99.7% my target. Optimum may lie between 99.7 to 100% somewhere. I don't care. So now you see he's right, that if you want to solve this problem and say your goal is to find the optima, you may have to wait an exponential time. You cannot find so quickly. That 30 minutes would have been 3 years or something. But that extra from 99.7 to the optimal, which could be close to 100%, to get that benefit, you have to spend exponential amount of time. So these practical problems had that kind of feature. But if you come and put your engineering hat, and say, okay, I'm not interested in the optima. Who cares about 2 kgs of error? If you can give me such a solution, I'm happy. Then we can go and look for algorithms or design a method design an algorithm that can have this kind of polynomial time algorithm, right? So this is one of the few examples where such a large number of variables have been solved. So I'm going to skip, in the interest of time, few things now, because what I've done so far, try to give you an idea of what is an evolutionary method and some of the practice, the use of those, and some of the problems that I have solved with showing that the problems from practice may come from 3 variables, but could be complex enough for classical methods to be used, or simple problem, linear, but the number of variables, the dimension of the problem is an issue. So in both these cases, evolutionary methods can be a good strategy. Let me skip some of these few things that I'm saying here. Evolutionary algorithms can also be used for real parameter optimization, and these are called real-coded GAs. There, what you do is you have 2 parent solutions, use a probability distribution to compute children, to create children, and then you go from there. Because it's not a binary string anymore. You have numbers, so all you have to do is basically do blending in such scenarios. Okay, before I go any further, may I know how much time I have for this lecture? I was not keeping track on the time. Is I'm already up, or? So I can plan my rest of the thing. About 20 minutes for this lecture. Good. All right. So that's gives me some time. All right. So again, I'm going to then skip some of these. Okay. I'm skipping some of these details about when you have real parameter optimization. But let me talk a little bit about DE, and I'm going back, DE and particle swarm optimization, because these are getting to be very popular methodologies in evolutionary computing. They are used for real parameter optimization. So that means all your variables are real numbers, okay? And you're trying to optimize an objective function with constraints. So differential evolution came in about 1995, almost at the same time the real-coded GAs were developed. The way it works is the main thing you have to think there in real parameter optimization is how do you create a solution? Because all you have are real numbers. So how do you create? So the DE, the way it does is it takes 3 solutions. First 2 solutions, for example, here I'm taking x2 and x3 and making a difference vector between x2 and x3, and then multiplying it with a factor called lambda. Usually it's less than 1. They use usually 0.9. And then that shortened vector is added to the first variable. So basically there are 3 parents, x1, x2, and x3 you take from your current population, take a vector difference of x2 and x3, reduce it by this factor lambda, and then add the resulting vector to x1. So you get a new point. And here this new point is called v. Now what you do is you choose a fourth variable vector. Usually it's the best individual in the population, and you do some kind of recombination, some kind of crossover between the v and that best solution. So that means some of the variables in your child solution, some of the variables you pick from v, some of the variables you pick from your best population member. So that's what is differential evolution. And that new child is put back into the population. So this is called a steady state way of doing evolutionary computation. But they have been very successful simply because they are considering the best. So this has some grittiness in it. And we had compared some of these methods with some other real parameter GA that we had developed. And they do fairly well. The other one that's also very popular called particle swarm optimization, or in short PSO, what they do is, again, there are 3 parts of this. I'm showing you in this highlighted line here. So your current solution x is changed with a velocity called v. Okay? And this v is computed with 3 terms in it. One, that's his previous v, the already v that he has. And then there are 2 other terms. One that comes from the difference between the current point with that individual, that population slot, whatever was the best it had since the beginning of your starting the run up till now, whatever is the best point you went through, that difference multiplied by a random number and multiplied by a constant c, c1. And then the second part has more of a global part, the social part of it, where it's the difference vector between you and the current best solutions, considering all population members. Again, multiplied by a random number and multiplied by another constant called C2. So basically, what you're saying is, you can think of this way, it's a swarm of points that are flying, and every individual point in that is getting attracted towards its previous best and also getting attracted towards the best of the population ever it went through. And then you are creating a resulting vector in which you should go, and that vector v is added to your current point, and you get the new point. So there are a lot of other issues here. There are multi-swarm kind of ideas. How do you choose this C1, C2? These are important factors, but this is generating a lot of interest because of its direct similarity with what goes on in nature, with school of fishes, the way they fly, the way they swim, and the birds. You must have seen in the sky sometimes in the evening time, these birds will flock together, suddenly change directions. So this whole simulation of that is kind of reflected here in particle swarm. Only thing is, you're now putting some kind of a reason why they are flying like that. You're saying that all these particles together are trying to go towards the minima of an artificial objective function that they have. In the case of birds or fishes, they may have an objective that they want to go to someplace, to their nests, or to a safe place, or whatever. So, so these are very meaningful symmetry, rather simile that you get from nature. This one here is getting very popular. It's called CMAS, covariant matrix adaptation. It's a very carefully designed algorithm where they run an evolutionary strategy for a few generations and collect the good solutions that you've got till that far. And they actually do a mathematical analysis of those points and figure out which directions are better using a principal component analysis. And then for next few search iterations, you are going to be using on those principal directions. So they are more sophisticated mathematically than, and less nature inspired than some of these other methods that you have. So all round developments are going on. It just depends on what is the background that you have, how you view these kinds of very free, open algorithms that you can mold it, you can change it the way you feel like. All right? You can use these methodologies in a mixed way. Like if you have some variables that are discrete, some variables that are continuous. I'll show you with an example here. Let's say this particular component will come somewhere in your design, and you're doing a mechanical engineering design, for example. And this is a rod that has come somewhere there, and you're trying to decide a few things. One is, am I going to have a circular cross-section, or am I going to have a square cross-section? That itself is a decision variable. You have not decided yet. So in a genetic algorithm representation, you can use a bit, one bit, to represent these two outcomes. If it's a 1, that bit is 1, you say it's a square cross-section. Or if that bit is a 0, you say it's a circular cross-section, right? So just this one bit allows you to keep that as a variable. Now the next number is interesting. What I have here is 14. That's the dimension of the cross-section. So it depends on what you have before. So if the before bit is 1, 14 says is the side length, is the length of the side of the square. If the previous one was 0, the bit was 0, that means it was a circular cross-section. 14 says this is the diameter of that circle. So you see, one variable is kind of linked with the other one that you have, but these are all allowed in GA. You could do that. The third variable could be the length, and that could be a real number. And this number 14 can be only integer, so it can only take integers, for example. And the fourth one is really interesting. I want to put now material option also as a choice here. So let's say I have got a choice of 8 materials here. Steel number 1, steel number 2, copper, aluminum, zinc, whatever, I have it there, right? And now I'm saying I'm going to give a code to each of them. Since there are 8, I could use a 3-bit string coding for these materials. 000 means still number 1, 001 means still number 2, and so on and so forth. And now this particular representation that I have, see what it does. It says this element that we have is made out of aluminum, because 101 is the code for aluminum. And it is square cross-section. It has a side of 14 inches, and then the length is 457 inches. So if you want more features like tapering or other things, you can keep on adding stuff there. So this kind of representation is very, very flexible. And then you can run your GA with this mixed type of representation very easily. Very lately, we started working on these concepts called bi-level optimization. So this is really the 2-level optimization, but probably 1,000 level harder than doing the single level optimization. There's not many literature yet, but these problems very often appear in practice. We're just solving a greenhouse problem now. It's a control problem. So many of you may be of interest to this problem. So in any control problem, you have some control parameters, and you have some control variable, let's say, and you have some controlled variables. Like in this case, for example, my controlled variables are how much I should put as the temperature inside, or some other set points, humidity level I should put inside my greenhouse. So these are my controlled variable, and my control variables are, how to do this, how much air to pump in, how much ventilation to allow, and so on and so forth. So you can consider this problem as a 2-level problem, where upper level, you have all these control set points, control variable set points as your variable. You are just trying to decide, how do I set temperature, humidity, all these different things, without knowing how to achieve that, but you're just setting up. And you're trying to optimize, let's say, the overall cost, energy cost of running it, and of course the production, because you want a lot of productions to take place. So, and the lower level, you are trying to achieve those set points from the upper level using this control. You're saying now that's where you're solving you're doing most of your computations. You're solving PDEs or ODEs to simulate the whole control systems, and at the end, you get those target values, and you match with those set points and send the error, or you could do time or accuracy. That's the error I'm saying, accuracy for given environmental conditions, like how the humidity is changing externally, temperature is changing externally, of course, not in your hands. So those are, of course, given, but then the whole control system problem is split into 2 types of problems. There are 2 optimization. There is an upper level optimization, which you're trying to do upper level variables like set points. And once you have those, you go to the lower level and then you try to achieve it and figure out how to control your control variables so that you achieve that. So it's a very fascinating area. You could do it to any other designs as well, where there are distinctly 2 types of variables, and you can split them up into different bi-level problems. So this could be a very exciting thing to do. The other thing is meta-modeling. As I said, there are lots of problems in practice which requires computationally more and more time to evaluate. For example, you need to call a finite element software, or a CFD solver, computational fluid dynamics solver, or some other processing software to evaluate what is the objective function and constraints. And they could be time consuming. So there are methodologies where what you do is you take a sample of your search space. So a few points you take and try to fit an artificial surface through it, and then use that artificial surface for a few iterations of your optimization algorithm before it is no more usable, because you are now getting into a narrow part of that search space. Your original surface that you've created is no more representative. So there are a lot of methods like kriging, radial basis function, quadratic approximation, response surfaces, a lot of different methods that are coming out. The kriging and days in this particular idea is pretty good. There are other methods called ego that are coming out to be excellent algorithms for this. So what these methods can do is can predict you. Like here I'm showing you the dashed line is actually the actual function. Let's say it's a single variable function. The red line is what the kriging predicts with the few points that are evaluated. And the shaded area there actually says what is the error, maximum likelihood error that you may be doing. Because at the points you're evaluating these solutions, there is 0 error. But elsewhere, there is a non-zero error. So, but these kind of methodologies have this ability to not only tell you what is the prediction, but also tell you how much error you may be making. So using these 2 concepts, you can then come up with an expected improvement of your function based on probability and statistics. And then you can predict where do you put your next point so that you can reduce these uncertainties in your error predictions, okay? So there are a lot of such methods that are coming out, which are coming out to be very fast methods for solving these problems. Again, there are problems in practice. I showed you how much massive multimodality that a 3-variable problem can have in practice. If you have so many multimodality, it's very difficult to really solve rather than having a very global perspective to your algorithm. But not all problems can have such massive multimodality. There can be some problems where there are few optima, let's say 10, 20, 30, 40, 50 optima. And some of them are global optima, some of them are local optima. Your goal is, of course, to get to the global optima, but how do you find them? And your goal is also not to get the global, but as many global optima as there are, or maybe some global and some local optima that are widely separated from each other. So when you have such a problem, you need to think of evolutionary methods, because the main reason is that evolutionary methods work with a population of points, and when you're trying to find multiple optima, you can then capture multiple solutions into your population, because your population allows you to store them. So there are some methodologies based on natural niching methodologies, niching and speciation methods. The fact that we humans and animals and amphibians and sea creatures are all co-surviving in this world is an interesting phenomena. And if you look at how we are co-surviving, is that we are sharing the resources. We don't go and disturb the animals in the forest that much. Then if we had done too much, then one of us would have survived, right? Whoever is the strongest or wisest or whatever would have survived. But then the fact that we said, okay, we're not going to intermingle with them, let them survive there, let we survive here, you can consider us, animals, amphibians, all these maybe are different peaks in your problem. So if you can somehow mimic this sharing concept in a genetic algorithm, artificial in a computer algorithm, you may be able to maintain multiple solutions co-surviving in your population. And back in '89, actually, we showed that this idea works with this function called niching function or sharing function. Here is an outcome from that on a very simple function. If you're trying to solve this problem on the left side, where there are 5 optima, maxima in this case, if you don't use anything, use straight away the genetic algorithm, that's what happens. Every population member eventually goes to the best solution, okay? But if you introduce our sharing strategy into the population, look at what happens. The whole population now gets distributed. So there are 100 members in this population. In the left case, all 100 of them are in one place. In the right case, all these 100 individuals are proportionately put by the algorithm to different peaks. So that means when you terminate this run, you will not get 1, but all 5 optima. So you can simultaneously optimize for multiple solutions. So these are fantastic offshoots of GA. When you're solving scheduling kind of problems, you have to think a little differently. Your recombination and mutation operator should be different. So we came up with some very neat ways of doing it. Again, for the interest of time, I'm not going into the details, but you can look into some of these work if you're interested, how to come up with a placement. The problem comes in this is if you have 2 designs that are very good, let's say it's making a perfect placement of things, because one of the problem here is that if there are 36 members, like here I have, every element should be put and then put only once, right? So if you think of a TSP, like traveling salesperson problem, where a salesperson has to travel to various cities, every city it has to travel, and then only once. So this kind of restriction is there. So when you have 2 parents that have a perfect schedule like that, and when you recombine, you may screw up. You may get a child solution that's not a feasible plan. It's not a feasible schedule. So then you are in trouble. So you need to think of some ways of doing recombination that will guarantee you that you are finding another valid schedule. So that's the only thing you have to take care of. Lately, we have started looking into problems that are variable length. In fact, we looked into the optimization mathematical literature. They have no clue. They have no ways of representing an optimization problem like that. Here, the number of variables of a problem is changing. So let me give you an example. Here is one. We have a square region, it's a rectangular region, and we are trying to cover it with radars. Let's say mobile networks. So they're mobile hubs we've got. Every mobile hub has a particular circular radius that it can cover. Okay? Now, we don't know how many mobile hubs we should have to cover the whole thing. But obviously we'd like to minimize because it costs, right? So can you find the optimal placement of the mobile, so XY coordinate of these circles, and how many of these circles? So I can have one solution with 30 circles, okay, with a little bigger radius, maybe that's covering. Another one, I may have 40 circles with slightly smaller radius and covering. I don't know which one is even good. So at this point, I'm keeping it flexible, that I don't want to tell you exactly how many circles you should have. You choose, but tell me the overall minimum cost, because I tell you, if you do so many circles with such and such radius, how much is going to cost you. So I'm interested in the overall cost. So this becomes a problem with a varying dimension, and we get this many times from practice. There are really not many good algorithms. In fact, the whole optimization literature doesn't exist for such problems, but these exist in practice. So we came up with some GA to solve such problems with different kinds of representation and recombination operators. You can see that some of them do not work very well, like cut and splice is not working very well. It's requiring 70 circles. Then the synapsing crossover is taking 42 circles, but the one that we finally liked and kind of working on many other similar problems is the gene preservation concept. In this case, we record only 32, and you can see how nicely distributed these circles are. Okay, so these are interesting areas for doing further research. Multi-objective optimization is our next topic, so I'm going to keep it for that. But here, just want to tell you that so far, whatever we talked about, we had one single objective function, okay? Every solution, when you evaluate, you get one objective function, and that drives the whole search, one fitness function. Here, in these problems, we don't have one, but more than one. So for example, if you're trying to buy a car, you say, okay, my pocket is important, right? How much I can afford. So cost minimization is one thing I have in mind, but whatever solution you give me for minimizing the cost may not be the car I'm looking for, because I have some other issues like quality, comfort. These things are important to me. So if I optimize now for comfort, I get some car that may be 10 times more expensive than what I can afford. So what is the solution then? When I have both objectives are of interest and they are in conflict to each other. So I will talk about these kinds of problem solving in the next, and this is really, again, an area where evolutionary methods have a niche. And we've been working this for the last 20 years now. Lots of literature out there, many ways you can solve these things. I want to finish up my first talk here by talking about some theoretical results which are good to know. Population size is an important thing when you're doing evolutionary methods, because you're dealing with a population of points. Important thing comes in is, what is that size? How many population members you should use? So usually, the thumb rule that comes from the theory says should be proportional to the number of variables. You should use a high crossover probability and low mutation probability. Okay, there are some reasons that are given here, but the whole evolutionary algorithm is an act of exploration versus exploitation. How much exploitation you are doing to your current population and how much exploration you are bringing in through your recombination and mutation operators. You need to just make a balance of that. That's the real thing. When you're designing new algorithms, you need to keep that in mind. Your mutation should be an operator that can take you from one point to any other point in the search space. Then you have a convergence property, actually. And crossover is found to be useful in more complex problems. Mutation is useful for simple problems. You may not need crossover for those problems. But if you have a complex problems, you can't just solve it using mutation-based methods. Anyway, that's a theoretical thing. But the last one is important. We have a proof, asymptotic convergence proof for this evolutionary method came by Rudolph in 1996. It says that no matter what problem you're solving, as long as you have a mutation operator, that has this property that it can take you from any point to any point in the search space with a non-zero probability. And you have an elite preservation, which means your current best solutions you are never deleting. You're always passing on. This algorithm will always converge to the global optima. There is a proof. But this proof is useless to me, being an engineer, is that it doesn't say when. Is it going to be today, or is it going to be 100 years from now? I don't know. So as its practical implications are not much, but it kicks many people. Many people think, wow, that's a good thing to have in an algorithm. So I'm using an algorithm that has an asymptotic convergence proof. Simulated annealing is another method which has this kind of asymptotic proof. So the question then is, since we don't have a rigorous proof for any arbitrary problem I'm trying to solve, and actually the NFL theorem says that, you cannot have one algorithm solving all your problems with a proof. NFL says that. So don't even try looking for that. What should we do in those cases? Because today I get a problem from one industry, tomorrow I get a problem from another industry. What can I do? Because I cannot prove that whatever I'm giving for any problem is an optimum, right? So there are a few things you could do. First thing is you try again and again. You try a few times and come up with some kind of statistics to say every time you're getting at the same place. Like I showed you in the case of Spain's energy system, energy company problem that I showed. Every problem we do that, okay? And then compare with other methods. So you need to be able to statistically show that the results you are getting are coming every time you use it, and there are not much improvement you can make from it. So these are some ways, and when you go to multi-objective, you can say a bit more. We have also done some KKT optimality-based termination conditions to say that if you're solving problems that are differentiable, we have methodologies by which the guarantees that you are close to the optima. But those are very specific problems that you can try for. So to conclude this lecture, I want you to recognize first what problems are optimization problems. And in the beginning, I showed you the scope of different problems that are ideally optimization problems. So first thing is the recognition, because sometimes you are going out from here, from being a student and working in a company, you get a problem today, you wonder, what problem is this? What method shall I use? Is it a root finding problem, or is it that I have to solve it using a partial differential equation solver, or is it an optimization problem? What is it? First of all, you need to know that. Second is, once you've recognized, oh, it's a problem I can solve through optimization, don't shy away from using an optimization method. There are quite many algorithms available, but some of them will work, some of them will not. So you need to have an idea of this kinds of problem, what methods are good. Because I'll tell you, if you're solving a linear problem with no complexity, you should not use this method. I'm telling you again and again. There are very fast provable methods that are available. So, but you should be knowing these things when if you are in the optimization business. Evolutionary methods, you should think when you have more and more complex stuff in your problem. Most likely, there doesn't exist a provable method from classical literature. That's where you have to use. But I always use this principle. First, I try a classical method, although there is a proof or not, and then see what happens. And then I try to customize a method using evolutionary method. They work because of their population approach, because the procedures are so flexible. You could use parallel computing, something I didn't mention at all. These methods are highly parallelizable. So if today's world, GPU computing or even parallel computers are very easy, cloud computing. So you could actually use those facilities very nicely because these algorithms are highly parallelizable. But customization is the key. The other thing is that I am facing again and again talking to people in industry is this, so I recently joined MSU, right, about 2 years ago. The other day I was waiting for a lift in a different department because I'm trying to work with a professor from plant sciences, and I'm in engineering. So I went over there, waiting for the lift. There was a guy coming from the other side and asking, oh, you are the optimization guy, right? So I felt good that somebody recognized me with my profession. So, but I thought I saw him, but I couldn't make out who he was. But he then introduced himself that he's a professor for plant sciences. But then immediately he told me that in his field, optimization doesn't work. And then he left. I get these things so many times from industries. I think there is a communication gap of what they mean as optimization or what I mean as optimization. So I think that's probably true with many people that I meet, particularly students who didn't go through a course or some kind of a workshop on optimization. So this is a good platform for you to get some ideas that what these methods are. Because in practice, when you say optimization, people use this word very loosely, that, oh, I have optimized. And if you ask them a little bit that, what do you mean? What method did you use? He will wonder and say, no, I didn't use any method. Then what? Oh, I've compared 4 or 5 solutions and found the best. That's not optimization, right? So that's what they mean. And sometimes they think, oh, I have done a cost minimization and I found the best cost solution, When you go and find that, oftentimes that's useless, because that's not what you want to do all the time. If you have done that, anything you see around us, there won't be any quality. Everything will look so cheap that you use it one time and then you have to throw it. But we don't see those things around. That's because it's never the case that we are interested in a single objective optimization. So if you're only doing single objective and you're showing the world how good optimization is, you will only get these kind of comments from industry people who are practical people. Will say, no, no, I don't want to do these things. I have more than one objectives that are in mind. So the next lecture would be talking about that and how you can handle multiple objectives. Okay, so I'll stop with this, and if there's some time left, I would like to take some questions if you may have.
Thank you for your presentation, Professor. Could you please recommend for us a book or any material for B-level optimization?
Okay, this is a good question coming out to be a recent topic rather. There is one book by El Ghazali Talbi, T-A-L-B-I is his last name, from Spain. He has compiled the book where a lot of people, so it's a multi-authored book. That's the only thing I can think of. And there is one on theory by Dempe, D-E-M-P-E. He's doing most of the theory in bi-level. These are the two books I can think of. But we started bi-level optimization work about 3-4 years ago, so we think we have enough material. So hopefully there will be a book coming from our group in a year's time, but we are in the process of doing that. We have a website created exclusively in this area. It's called bilevel.org. So if you go there, bilevel.org, you will find lots of materials. First, introducing what are these bi-level problems, different problems that are bi-level. Some MATLAB codes are also there. Our methodological BLIC is available there for you to use, and some important papers in the area. And if you are really working in that area or want to work in this area, my student who is now the moderator of that, called Ankur Sinha, if you send me an email, I can forward you his email address. Or if you go to this website, bilevel.org, you find his email address. Send him a note that to put your name into this as an interested person in this field. So we are trying to also collect all those who may be interested in this area. So it's a good time to be in the field because there's not much out there and so important in practice that we'd like to gather more and more people and kind of move it forward.
Thank you.
All right.
Question?
Thank you, Professor.
Yeah.
Being you a specialist in evolutionary optimization, why you choose this method as a second option?
Oh.
Why classical?
That's a good question. We could be doing for so many years. Why do we still do it as a second option? Yeah. My simple reason is this. The classical optimization and the literature is much older than when we started doing it. Okay, we started only, as I said, from 60, but the optimization is used only in 75, was suggested. Real application started in 80s. And before the Second World War and even before, optimization were used. So we came in to this field and showing that, okay, we leave you with certain problems. We cannot do anything there, and we don't need to because you have provable methods. But there is a whole lot of other problems that you don't have a proof. So that means any two method can fight there, can come up with what can work there. And that's what we are showing, that more and more complex the problem are, the better could be using these methods. So the fact that we entered later, so there is this question then comes from reviewers, particularly when you're sending it to an optimization journal. Definitely there's going to be a comment like that saying, why did you use evolutionary method? Why didn't you use a classical method? So we've been tired of answering such questions for every problem that we solve. So I think it's kind of gone into our head that we have to do this as a second method, because if there exists a good solution that I got from the classical method, there is no need for us to do any of these things. But believe me, I have worked with so many industries, so many practical problems. Except once or twice, it didn't happen that we were happy with what results we were getting with the classical methods. But that's not to say that those are not good. I have hybridized, I've not shown you here, hybridized classical methods with evolutionary methods, so that you start with the evolutionary method, end up with a classical method. Sometimes we use a classical method as a mutation operator. That means now you have one point you want to mutate. You don't need too many points. So you can use a classical method with this point as a starting point and use few iterations of that. Often we found those are wonderful to mix the two things. So don't take me otherwise, that I hate those methods. I like to use them in my methodology. I like to use them when they have a clear niche. But it's just that there are so many other problems when you use them, you don't get the satisfactory results. Then where our methodologies come in. Okay?
Thank you very much for a nice talk. You talk about using GAs or EC methods. And you talk about the customization, that the key to be successful in the application. What are the basic guidelines for doing a good customization? Because it's kind of an art to apply the technique.
It's a science and art, both, actually. They call the customization issue, simply because the theory says you cannot have one method, one scientific method that's going to be good for all problems. So now you can apply, you can come up with a method. It'll not probably going to be the best. So some problems you will go there quickly. Some problems it'll take lots of time for you to get there. If you are really biased and say, no, this is the one I'm going to use all the time. So I think the clever thing to do there would be to then customize for your algorithm for the problem. Now that means to know a little bit about what is this problem that you're trying to solve? What are the building blocks of this problem? That means what are the essential things I need to have as a part of the solution, or as a way to create good solutions? Okay? So just to give you some idea about the casting sequence problem that we solved, it's a linear problem, right? So one of the features of linearity, or any linear problem, is that linear superposition principle holds. That means if I have a part of the whole solution right in one solution, another part is right, right means let's say very close to being optimum, in another part of the solution, if I recombine them into one, I'm expected to get better results, because that's the property of linear superposition. So that's an idea I'm using from the known literature, using that in my crossover operator, so that I find the right place for them to be cut and take these components from different parents and put them into one. And that's how I'm jumping in the search space, because now good things are happening. But if the same idea, if I take and solve a nonlinear control problem, for example, this may not work, because something that was good in one solution and good in another solution, if you join them, it may not remain good, because there are nonlinearities, there are interactions. So I need to think of some other way. So in the literature, although I'm saying customization is the key, there is no systematic guideline pointing to a particular problem solving, so that you can take from there and just follow that. But there are some overall guidelines in the context of building blocks, in terms of thinking the operators, what should be respected and what should be not, the guidelines in terms of population size, the guidelines in terms of termination criteria, in terms of using these hybridization, that, one thing that we often do is repair. So I've created a solution by some recombination. Now, instead of accepting it as a whole, I try to repair it based on some problem information. Okay? So any of these guidelines you're talking about involve some kind of heuristic. So that it's more meaningful, it's more contextual to my problem. So you cannot do these things unless you know a little bit about this problem that I have. That's my last thing that I have there as a line, actually. It says that a good optimization effort requires knowledge in mathematics, because if you want to do these things, like the linear superposition stuff, you need to know. If you don't know that, this idea will never come to you, right? So you need to have a little bit of idea of what is mathematics in optimization. computing. You got a good idea. If you cannot implement it properly, the Azure system is available. There are a lot of cloud other computing available. But if I'm not savvy about that, if I'm not good about utilizing this, taking advantage of that, the data structure that I could use, my code is not going to be very efficient, and it may take me a lot of time, and this may not be acceptable to the industry. Saying you're solving a problem taking 1 month, I cannot use it. But it was probably just utilizing the memory or writing the code in a little better way. And of course, the application domain information. That's the thing I'm highlighting, is that you got to also know, being an optimization person, you also ought to team up with some people which has application background. So I think a good team for doing such problem in practice is a person who knows optimization. Hopefully that person also knows about math of optimization somewhat, algorithmic issues of optimization somewhat, and then a person from the application area. And then hopefully this team is okay because they have the adequate computer background. But if you are like me, a professor doing only algorithm development, not knowing much about the nitty-gritty computer coding stuff, I would like to have my student who is good in that also in the team. So I think it's a team effort. Different expertise is needed to get the customization, but the case studies that we have in the literature can be a guidance of how such a thing was used in this problem or in that problem. That's how it remains as an art, okay, so far, and I think it will remain for a while. But I have been solving with different problems with various companies coming from different fields. So I could see that some ideas I used before, I could implement it there, and oftentimes that remains as a shortcut of solving that problem. So I think it's a long way of answering your question, but that's something I think we need to work more on, maybe identifying problem classes and identifying corresponding customizations that have reportedly been worked and why they have worked. So this could remain as a very good compilation if we can do someday. It's a good question.
Let's thank Professor Debbie for the first part.
Thank you very much.
The second part of this lecture will be within 15 minutes.